All right, there were some questions on 6.1. Okay, some stuff like this, where you were given a geometric formula, in this case for the volume of a sphere, and then you were asked to rewrite, I can wait if I need to. You were asked to rewrite the volume formula in terms of a different variable. In this case, we're told that r equals x over 3. So you were asked to plug this in for r and then simplify it. So you're going to rewrite the volume formula in terms of x's instead of r's. Okay? So how do we do that? There are a couple of them like that you were asked to do. What do you think? This is the radius, right? Of the sphere.
Plug it in.
Yeah. So we're going to plug in the quantity x over 3 for r in this formula. So 4/3 times pi times the quantity x over 3 cubed. Okay, now what do we do with that? Okay, good. We're going to follow those properties of exponents. We're going to distribute the 3 to the x and the 3, and that gives us 4/3 pi times x cubed over 3 cubed, right? Now what is 3 cubed? 27. Good. Now you probably wouldn't have to show all these steps, but we're going to write them all out. And then what? What do I do now to simplify that? I'm just about there. But do I need to have this? I got a 3 there and it's kind of awkward. I don't need to have 2 separate denominators. What would I do?
No, I'm not answering that.
Okay.
I'm just really confused right now.
Okay, what do you think? Okay, now if we were adding or subtracting, we would. But when we're multiplying fractions, what do we do? If you're adding or subtracting, right? Then we got to get a common denominator. Okay, if we're dividing, we'll flip and multiply. I mean, you're on the right track. Let me give you. This will jog your memory. What if I'm doing this? What if I'm just multiplying 2/3 times 1/5? What do I do? When I multiply fractions, I multiply. No. Straight across. Yeah. Multiplying fractions is the easiest thing we do with fractions. We just multiply straight across. So 2 times 1 is 2. 3 times 5 is 15. Now, if we're adding those or subtracting them, that's harder. Then we got to get a common denominator, and that's a little more of a production. But multiplying is no big deal. We just multiply straight across. So if we multiply straight across up here, now the pi, what about that pi? Where does that go if I'm multiplying straight across? In the top or the bottom? In the top, right. In fact, if we want to, we could even write that. How about if we do this? Let's write that as pi over 1. You can always think of it that way. So now when I multiply straight across on the top, 4 times pi times x cubed is just 4 pi x cubed. We always want to have the numbers first, then the constants, then the variables in alphabetical order. On the bottom, 3 times 1 times 27 is just what? 81. So that's our answer.
How would you write that in the calculator?
Okay, in like Moodle? Okay, so in Moodle, we could write that maybe like this. There's a couple ways we could do it, but we could write it like the quantity for pi. And I think sometimes they want it as a p. Is that right? Is that how they were asking you to do it on there?
They didn't really say.
On those questions?
It said p.
It said p. I think it said p. Yeah, so 4 times p times x cubed divided by 81. something like that. And I don't even think you'd have to have the parentheses. You wouldn't. I mean, I believe it would mark it right even if you didn't have the parentheses. I would put them there because then it puts this on the bottom and everything else on the top. Okay. How about, while we're at it, maybe let's look at another example from that section where we're talking about properties of exponents. Let's pick a harder one. I think things are going pretty well with that. Okay, so how about one of these? What if we take something like we want to simplify that expression. And there's no one way to do this, honestly. There's several different orders in which we could do the simplifying. Here, we could apply the properties of exponents. I personally think it's easier to just, at least with the variables, just multiply straight across first and simplify the whole top and the whole bottom. And then you can align the various parts vertically and simplify. Okay, so by that I mean we could just multiply straight across here and get an answer, multiply straight across here and get an answer, and then we could simplify top and bottom. There is one thing though, I mean, to me, there's another thing here with the numbers that's a little awkward about that. If I multiply 12 times 7, I'm going to get a big number, right? 84 over 7 times 4 is 28. 84 over 28 certainly can be reduced, but you got to think about it a little bit to reduce it. Remember that if we're multiplying numerical fractions, let's just deal with the numbers for just a second, because that is the hardest part. It may not seem like it at first. When you look up here and see all those variables, you're probably anticipating that the variables are going to be the hard part. Not at all. The variables are very simple, as we'll see, and you've probably already come to that conclusion in working on this assignment. It's the numbers that are the hard parts. It's the non-algebra stuff here that's really the tricky part. Multiplying those numbers straight across, if we were just to focus on the numbers, what would you do if I have 12 sevenths times 7 fourths? Any suggestions how we can do this most easily? We could multiply straight across and then reduce. What do you think, Kyle? Yeah, let's simplify. The thing is, we're multiplying fractions. Now, if we're adding or subtracting, we couldn't do this. But if we're multiplying, things get a lot easier. We can cross-cancel them, right? So, for example, 7 over 7 reduces to 1 over 1. That's good. 12 over 4 reduces to 3 over 1. Okay, so now if I multiply it straight across, I would just get 3 times 1 over 1 times 1, 3 over 1, which is 3, right? Okay, we can do that. There's no reason not to. So up here, we could turn this into a 1 and that into a 3, that into a 1, that into a 1. And then when we multiply straight across, let's see what we get. Now the number part is just going to be a 3 on the top. What about the variable parts? Okay. If I multiply x times x to the 5th, if I'm going straight across now, what power of x do I get left with? No, if I'm adding or if I multiply like bases, what do I do if I have a to the m times a to the n? What do we do to the exponents? Add them, yeah. Right, you multiply like bases, you add the exponents. Okay, everybody getting this? Because I want you guys to be aware. I think some people are falling behind a little bit. You can probably catch up at this point, but we're going to be testing over this stuff. It's not that far off, really. So don't let yourself, if you get behind now at this point in the year, it's really hard to catch up. So don't let yourself get behind. If you haven't wrapped up the Chapter 5 stuff, I mean, you got to get on this. I'm just giving you a little heads up right now before it's too late. So what about this then? We have x to the 1 times x to the 5. X to the 6, sure. Okay, we're going to add the exponents. Y to the 1 times y to the 3 is what? Or y to the 2, sorry. Y to the 3. On the bottom, I've just got a plain old x to the 4th. I've got a 1, which I won't write, right? I get 1 times 1 is 1. X to the 4th, and then y, which is really y to the 1. So when I multiply straight across, after reducing all the numbers, that's what I'm left with. Okay? Now let's get rid of this stuff. And what can I do here? Now, notice that I can line up the numbers and the x's and the y's. I can line up all the like bases. So when I line up the x's, for example, what is x to the 6th over x to the 4th? What do I do when I divide like bases? Subtract, yeah. So we're going to end up with, I've still got my 3. X to the 6th over x to the 4th is x to the 6 minus 4. So x squared. And then what about the y's? Yeah, y to the 3 minus 1 is y squared. I don't have anything on the bottom there. I don't need to put anything there. There's a 1 there, but we wouldn't write it. So that's my answer. Okay? Make sense? Okay. What about, while we're at it, let me just do, there's one other one. It seemed like there was another issue that came up a couple times. What is this week? Okay, what about that one? Can I reduce the numerical part at all? 3 over 7 is kind of stuck with that. Okay, so let's just multiply straight across then. I mean, there's really, it's already, we already did. I mean, there's nothing to multiply here. There's no, the x's are already all in one piece and the y's are already all in one piece. What we've got to do is just figure out what ends up on the bottom and what ends up on the top. I've got my 3 on the top and my 7 on the bottom. But what's going to happen to the x's, which are lined up vertically? Ah, okay, yeah. Now remember, when I divide like basis, and remember from our conversation, I guess it would have been, I remember when this was, Friday or Monday, I can't remember what day it was. We're going to deviate from the book a little bit here. The rule that the book doesn't really provide that I think is very helpful is, and you can kind of finish this for me, if I have a bigger base or a more powerful base on the bottom, in this case we're looking at the base x, I've got x squared on the bottom and x to the minus 3 on the top. The x's have more power on the bottom because 2 is bigger than negative 3. What do I do in that case? Yeah, good. We're going to keep the base where it has the most power, where the exponent is the biggest, right? So the x's are going to stay on the bottom. And what do I do with the power? X to the... Yeah, well, I'm gonna subtract the weaker exponent from the stronger exponent. They stay where they're the strongest. So we get 2 minus negative 3. Right? 2 is bigger than negative 3, so the x's stay on the bottom to the power of 2 minus the weaker exponent, 2 minus negative 3. Okay? So that fifth, right? What about the y's? Okay, 4 is bigger than negative 2, so the base y is going to stay on the top to the 4 minus negative 2. And so my final answer is just 3y to the 6th over 7x to the 5th. Right? Okay. Make sense? Okay. All right. This assignment is not a big deal at all. You just got to be familiar with those properties of exponents. Okay, what I want to look at a little bit. Well, hang on. Before I do that, let me do this. This is the one that I said I wasn't going to go through. I'm going to spend just a second talking about it, and not much. Adding, subtracting, and multiplying polynomials. Very, very, very simple stuff. There's nothing to this. When we're adding or subtracting polynomials, we simply combine like terms. That's it. This is real similar to, I mean, we've done this stuff with already in chapter 5. We've done some things like this. It's going to look really familiar. If I want to add these two polynomials, if I want to add them up vertically, there's really two ways we can do this, vertically or horizontally. If I add them up vertically, this is really convenient. The only rule you got to remember when you're adding up vertically, which is a little strange, is that you want to keep a column. I want to keep a column for each power of x. So I've got my constant column, I've got my x to the 1 column, I've got my x squared column, and my x cubed column. And if I keep them lined up like that, this is really simple. It's a convenient way to do it. So then we'll just combine these things vertically. Negative 7 plus 8 is 1. Negative x is all by itself. There's no x term in the second polynomial, so that just stays a negative x. 2x squared minus 10x squared, negative 8x squared, 3x cubed plus x cubed is 4x cubed. Done. That's it. Okay, so you're just combining like terms. If you line them up vertically, just put each term in its appropriate column. Okay? We can also just add these up horizontally, though. No big deal. What if I'm subtracting here? I'm going to just, in this case, what do you suspect you do based on what we did in chapter 5? Okay, good. We're going to carry the negative through, I heard people say. Distribute the negative and then combine like terms, right? So if we do that, if I distribute the negative sign, and they didn't do it that way, which I really, you know what, let's ignore what they do, and we'll do this our own way. If we distribute the negative sign through, what are we going to get? So here we've got our, do we even need these parentheses? No, because there's a 1 out in front, distributing the 1 doesn't change anything, so we can freely just get rid of these parentheses. So we've got 8x cubed minus 3x squared minus 2x plus 9. And now when I distribute that negative sign, what does it effectively do? Yeah, just good. Changes the signs of each term. So we're going to get a minus 2x cubed minus 6x squared plus x minus 1. And now we just combine like terms. Okay, so the x cubed terms, 8x cubed minus 2x cubed is 6x cubed. Let's cross those off. Negative 3x squared plus negative 6x squared is negative 9x squared. Negative 2x plus x. And then 9 minus 1 plus 8. Hey, can you, why are you guys talking? This is crazy. Go talk in the hall if you need to. That's fine, but just don't talk in here. 6x cubed minus 9x squared minus x plus 8, done. No big deal. Okay. All right, moving on. Skip through this. Okay. Just more of the same. If we add horizontally, in this case, because we're adding polynomials, just combine like terms. No big deal. Okay, what about multiplying? We can multiply horizontally or vertically. If we multiply vertically, you know, this just looks like multiplying multi-digit numbers is all it is. The only thing you want to keep in mind when you do this is when you multiply through. So I'm going to multiply just like I would if I were multiplying a 3-digit number times a 2-digit number. I'll just multiply the negative 3 all the way through first. Then I'll multiply the x all the way through and add up like terms. When you do that, you want the results to line up in those columns we talked about earlier, right? So we want to have a column for the constants, a column for the x's, a column for the x squareds, etc. You don't really have to write them that way up here, but when you multiply them out and you get your results, you want to put them into those columns so they all line up nicely. So negative 3 times 4 gives us our negative 12. Negative 3 times 2x gives us our negative 6x. Notice that we're starting to build these columns. Here's our constant column. Here's going to be our x column, etc. Right? Negative 3 times negative x squared is positive 3x squared, and there's our x squared column. And then we'll multiply the x through. X times 4 is 4x, so that's going to go in the x column. X times 2x is 2x squared, so that goes in the x squared column. X times negative x squared is negative x cubed, so then we got our x cubed column out here. And then we just add up vertically and we're done. If we just combine all those like terms, there's our answer. Okay? No big deal. We can also just multiply horizontally, that's fine. We've done stuff like this in the past. This just means distributing, right? It's easier to distribute from the smaller polynomial, meaning the one with fewer terms, to the bigger one. Then we only have to distribute twice instead of 3 times. So we can distribute the negative 3 all the way through. Okay. See, they're doing this goofy. I'm going to skip their stuff. We'll do it our way. So we could do this. We could distribute the, let's just distribute the x through first. Doesn't make any difference. If I distribute the x through, what's that going to give me? X times 3x squared is x times negative 2x. Negative 2x squared, I hear. X times negative 4. And notice that I'm putting these in those same columns again. And then when we add these up, I could just string these all out in a row if I want to. That's fine. And then add up like terms. Or I could also do this. I could take that negative 3. And when I distribute that, negative 3 times 3x squared. Yeah, why not do that? Why not line them up vertically? Negative 3 times negative 2x, and negative 3 times negative 4 plus 12. And then I just add them up vertically up there. Okay? Okay. Last issue, no big deal at all. What if we're multiplying out 3 binomials, or what do I do then? Yeah, well, I have to do multiply 2 at a time, right? So I could take, like, those 2, take care of business, get an answer, and then distribute this one through. Or I could use those 2 first, or those 2. It doesn't matter. Any 2 I choose, but I got to multiply a string of products in pairs. You always multiply in pairs. So if I FOILed out the first 2, I would just end up getting that, right, when I FOIL out the first 2. And then I could distribute the x all the way through and distribute the 3 all the way through. And if I did that, I'd end up with some answer after I combine all the terms. No big deal. We've done that stuff. Okay, here's the part I wanted to just pause a second on. We get some patterns. We haven't really emphasized multiplication patterns in the past because they've been pretty simple. It hasn't been a big deal. But now we're getting into bigger stuff, polynomials, and so these patterns end up being more important. We've seen this before. If we look at binomials, if I multiply a conjugate pair together, you know, a plus b times a minus b, where I've got 2 terms, and the sign between the 2 terms is positive in one case and negative in the other, and that always ends up being the first term squared minus the second term squared. When we FOIL it out, the o and the I will always cancel. And we've seen that before. That's probably pretty familiar. An example would be x plus 3 times x minus 3. That's a difference of sum and difference we're multiplying. We just get the first term x squared minus the last term squared 9. Done. Okay, no big deal. That one probably looks very familiar. Square of a binomial we didn't really spend a lot of time on. But here it is. We've got a pattern that says if we square out a binomial, we always get this result. So the quantity a plus b squared is always going to look like first term squared, so a squared, plus 2 times the first times the second, so plus 2ab, plus the last term squared. When we FOIL it out, that's always going to be the pattern that we get. And so it's quicker and easier now to start just knowing a few of these patterns that we see repeatedly, rather than having to go through the hassle of FOILing it out each time. It's quicker just to know that. It's not that big a deal for this one, but when we get to the cubes, it's a lot easier. How do we get from here to here? Rather than memorizing 2 formulas, you really don't need to. Look at it this way. What happens if b is negative? If we were to replace the b with a negative b, what would happen in our result? Well, a negative number to an even power is what? For example, negative 3 squared is what? Positive 9, right? A negative number to an even power is always positive, but a negative number to an odd power is going to be what? Negative, always. Negative 2 times negative 2 times negative 2 would be negative 8, right? So if I were to take this formula and I were to replace the b with a negative b, what would happen? Well, we'd end up with a squared plus 2 times a times negative b. That would become a minus 2ab, right? But the negative b squared would just turn out to be a b squared, right? So really all we've done to go from the top formula to the bottom formula is we've just substituted a negative b in for a b. And so you don't even need the bottom one. You really, you literally don't have to have it. It's never important. We could just, if we're trying to square out something like, let's say, x minus 2, then that's just the top formula where a is being replaced by an x and b is being replaced by negative 2. It's like saying x plus negative 2. So you could just use that top formula. So what would x minus 2 end up giving us if we use that top formula? If the x is the a, and the b is the negative 2, was that telling us x squared plus 2 times x times negative 2? What is that? 2 times x times negative 2. What's that going to be? 2 times x times negative 2. Say it again. Negative 4x. And then negative 2 squared would be 4. Right? So we could use this pattern right here to expand out that binomial without even having to have the separate one. You don't need it. Okay? Makes sense? If you want to, remember, and you can remember them both, it's fine. But you really don't need to. Top one, it works. Okay, and then the last step would be the cubes. Cube of a binomial. Okay, this one's a little bigger. Cube of a binomial, you get 4 terms instead of 3. That seems like a lot to remember, but the alternative is you've got to FOIL out a plus b times a plus b times a plus b, and that's no fun. So this is definitely better. Okay. Notice what this does. You can remember this, and you kind of look at what's happening here. Makes it easier. You know that when you're expanding out a plus b cubed, notice that the a's are starting with all the exponential power. So it's a cubed, and then there is no b. The a's are just gradually stepping down in power, so we go from a cubed to a squared to a to the 1 to a to the 0. We don't write it, but what is anything to the 0 power again? 1. So it's really there. We just don't write it. What about the b's? B's are going in the opposite direction. The b's end up with all the power. But if we work backwards, here they've got b squared. Here they've got b to the 1. Here they've got b to the 0. Okay, notice that the sum of the exponents, the a's and the b's, 3 plus 0, 2 plus 1, 1 plus 2, 3 plus 0, always adds up to what? 3. Right? So first term, all the a's, last term, all the b's, and they just kind of, one's going up, but one's going down. The coefficients are, 1, 3, 3, 1. Just have to remember that part. Okay, you get 3's in the middle for the middle two. But otherwise, if you see that pattern there, it's kind of easy to remember that. And same as before, you truly don't need the bottom one. You can just put in negative values for b in the top one, and it takes care of the bottom formula. So you get 2 for the price of 1. Let's just watch, let's apply that one once, see how it works. So there's the formula. What if we want to do an example like, well, we'll skip that one. What if we want to do, wasn't there a cube one? Was that a cube one? Oh yeah, it was, never mind, whoops. X plus 5 cubed. So we got to write down maybe our formula. What was our formula for the sum of, for the expansion of a plus b cubed? See if you can remember what it was. What was the first term? Good, a cubed plus 3, we had the number 3. A drops down, b bumps up, plus a to the 1, b squared, and then finally a to the 0, which doesn't even show up, all b cubed. Note there's symmetry with this one. Think of it this way too. There's another thing you can look at. There's symmetry here with the numbers. In the middle, I've got 3's and then 1's for my coefficients, right? So it's evenly split between first 2 terms and the last 2 terms. Okay, so then if we just do that stuff, if we apply that formula to this expression here, a is the x, b is the 5, plug them in. Right, so we just get x cubed plus 3 times x squared times 5, right, because b is 5, plus 3 times x times 5 squared plus 5 cubed. Right. So that just gives us x cubed plus, what about this one? What's all that going to become if I multiply through? 3 times x squared times 5 is 15x squared. Plus, what about this one? 3 times x times 5 squared. What's 5 squared? Times 3. 75. And then plus 5 cubed. 5 times 5 is 25 times 5. 125. Yeah. There's our answer. Okay. Let's try... one of these. What if I had this? What if I had 2x minus 3 cubed? Okay, let's follow same pattern. Okay, once again, what's our formula? A plus b cubed is plus good 3a squared b plus Good. 3ab squared plus b cubed. Okay, so let's try that. So then, oops. So what's our a in this case? 2x. Okay, so the a is the whole 2x. What's the b? What is it? -3. Good. Because that's like rewriting this as (2x minus 3) is the very same thing as 2x plus -3, right? So the b is the -3. We just follow our pattern. So a cubed becomes what cubed? The quantity 2x, yeah. Plus, what about this one? I get 3 times a is 2x. That's going to be squared times b is -3, right? Plus 3 times, a is, you told me, was 2x. Gosh, I keep my colors wrong. D was -3 squared plus -3, which is my b cubed. So what's all that stuff become? What is the quantity 2x cubed? What do I have to do if I take a product to a power? What do I do to that 3? I distribute to the 2 and the x, right? So that first term becomes 2 cubed is 8 x cubed, right? Second term, I'm going to get plus 3. Now, what's 2x squared going to be? Okay, good. So this part right here is going to become 2 squared times x squared. So that's going to become a 4x squared. So I get 3 times 4x squared times -3. So the numbers are 3 times 4 times -3. So how about -9 times 4? What's that? -36. And then I get x squared. What about over here? I get 3 times 2x. What is -3 squared? +9. Okay, good. So that one's going to be 3 times 2 is 6 times 9. 54 is the number part. And then I just get an x, right? And then finally, -3 cubed. -27. Okay. Okay, and that's it. Okay, make sense? Okay, no big deal. No big deal. All right, so that's, well, it took longer than I thought. That's all right. That's all right. Color quits there. I think there's a little bit of review there today too. That probably was good. Okay, so maybe that gives us an extra day, which is fine. You want to be, kind of catching up on chapter 6 stuff. We'll take a look at 6.4 later this week. Okay, and then 6.4 is a pretty big section. 6.4 we'll take half a week on it, just so you guys can be able to work on that in the lab a little bit. All right.